We're going to talk about Lewis dot structures. So here I have a picture of G.N. Lewis, and he started off, he went to Harvard, then later on he worked over at MIT, and later in his life he worked over in laboratories in UC Berkeley, and he was the head of the chemistry over there. The things we want to try to do are to be able to draw these Lewis dot structures. We have to kind of start for each element and find out how many valence electrons there are, and that's pretty easy. Then we're going to draw the symbol for each element. We're going to allow the different elements to share their single electrons, and then we're going to end up drawing the molecule. So we're going to go over that and then try a couple of problems. So here I have several different elements, and for each one of those you kind of need to say, well, how many valence electrons do they have? Now that's pretty easy. We can just kind of look at a chart, and everybody in the first column has one valence electron, everybody in the second column has two, and jumping over to the side, 3, 4, 5, 6, 7, 8, that's how many valence electrons there are. So we just take any element. Carbon, we know carbon is in family 4, so it's going to have 4 valence electrons, so we just put one on each side, and that's the symbol for carbon. If we try nitrogen, we know that nitrogen's in the 5th family, so we go 1, 2, 3, 4, and then we start doubling them up, 5. Okay, oxygen's in family 6, so 1, 2, 3, 4, 5, and 6. So we get 2 sides that have lone pairs and 2 sides that are just one-sided, one electron. Fluorine's in family 7, so 1, 2, 3, 4, 5, 6, and 7. Hydrogen, way over on the left, only has 1 valence electron, so that's easy. Silicon, we're going to find out that that's family 4, so it has 1, 2, 3, and 4, 1 on each side. Chlorine is in family 7, 1, 2, 3, 4, 5, 6, and 7. Sulfur is in family 6, 1, 2, 3, 4, 5, 6. And iodine finally is in family 7, 1, 2, 3, 4, 5, 6, 7. So for the different elements, you need to use a periodic table and see which family it's in, or just have those memorized. So let's try a couple of molecules here. These are the ones that we've seen on a worksheet. So if we take carbon, then I would start off by just writing a carbon. We know it's family 4, so we'll give it 4 valence electrons. And we have 4 hydrogens. So each of those hydrogens has 1 valence electron. And then our job is to match up all these individual little single electrons. It's very unstable to have them just open like this, so they're going to bond. And we'll bond these guys, and we'll bond these guys. Now if we want to go back and kind of clean it up, we put carbon in the middle, and then we have a pair of electrons to hook on the hydrogen, and another pair for another hydrogen, another pair for another hydrogen, and another pair for another hydrogen. So this would be the finished picture Lewis structure for methane. For water, we do the same thing. Start off with oxygen, and that's family 6, so we'll give it 6 valence electrons. And we can see we have 2 unshared electrons, and we'll do an oxygen. We already have the oxygen. We have a hydrogen, and we can put another hydrogen. Now we want to show these guys we're going to share, and those will share. They're sharing because they're single. Now we'll put them into a molecule, and we'll say oxygen, hook on a hydrogen, and we can hook on another hydrogen, and we still have 2 lone pairs. Now water, you see that sometimes drawn like this, so we hook on a hydrogen, and on the opposite side we can hook on a hydrogen, and then we still have our 2 lone pairs. Now when that sort of thing happens, we find out that the molecule water, actually does have a bent shape. So because it has that bent shape, then personally I like to use this shape, but both of them are correct. The last one here we have is ammonia, and so for ammonia we have nitrogen, 1, 2, 3, 4, 5. So we can see we have 3 places we can make bonds. So we have a hydrogen, and we get another hydrogen, And let's put another hydrogen over here, and we will share electrons here. We're going to share electrons there, and we're going to share electrons there. So we're going to clean up that molecule. Nitrogen bonding a hydrogen, bonding a hydrogen, bonding a hydrogen, and we still have that lone pair. Now we'll try some others. Here's oxygen. So we'll do the same thing. Here we'll draw our oxygen, 6. We have another oxygen, 1, 2, 3, 4, 5, 6. Now in this case, we can see, well, here's a pair of electrons that we can share, and here's another pair of electrons that we can share. So when we do this, we can go ahead and say oxygen, and we're going to put like 2 colons between the 2 oxygens. Those are our 2 shared pairs, and on each of the oxygens we still have a lone pair. Now those lone pairs could go top and bottom, they could go top and side, side and bottom. In reality they're actually kind of equally spaced, and what it really sort of looks like is 120 degrees, because the electrons are all negative, they're going to want to spread out a little bit. Okay, try nitrogen. Nitrogen's in family 5. 1, 2, 3, 4, 5. We have another nitrogen, family 5. 1, 2, 3, 4, 5. So we could share a pair of electrons here, and then these 2 could share, and then way around here those 2 could share. So when we draw that, we draw nitrogen, and we say 1, 2, 3 pairs of electrons, and each of the nitrogens still has a lone pair. I'm going to put them out on the sides, because since everybody is negative, they are going to repel each other and try to get as far apart, so they do make that kind of 180 degree angle. Now once in a while you see somebody draw it like this, 1, 2, 3, and that is also perfectly correct. Our last one here, OF2, oxygen, 1, 2, 3, 4, 5, 6, and a fluorine, 1, 2, 3, 4, 5, 6, 7, and another fluorine, 1, 2, 3, 4, 5, 6, 7. So we can see here's a single electron that can bond, single electron that can bond, and when we get finished, we'll draw oxygen, put on a fluorine, put on another fluorine, a lone pair on the oxygens, and some lone pairs on the fluorines. Again, I've drawn that at an angle because it really does exist at an angle, although if you drew it in a straight line, that's perfectly correct. You just have to realize you're looking at the molecule from the edge. Now let's try a couple of different ones. C2H4. So here we have our carbon, same exact system. But we have another carbon, and we have some hydrogens. Now one thing that we do know is hydrogens always end up on the outside, because the hydrogens, again, since they can only make one bond, then they have to end up on the outside. They can't hold 2 things together. So here we have several of the electrons on the carbons taken care of to hold on the hydrogens, and that still leaves us 2. So we can do there, and we'll do there. Now we'll clean this up. Here's a carbon. There are 2 pairs holding it together. Then there's a pair holding on the hydrogen, a pair holding on the hydrogen, a pair holding on the hydrogen, and on the hydrogen. Now the CO2, we would start off and say, okay, here's a carbon, 1, 2, 3, 4. Oxygen, 1, 2, 3, 4, 5, 6. And another oxygen, 1, 2, 3, 4, 5, 6. Now this carbon could bond onto a oxygen, and this carbon could bond also onto oxygen. Here this carbon and this oxygen, this carbon, this oxygen. So those electrons are going to share, and when we clean that up, we put the carbon in the middle, 2 pairs of electrons holding on the oxygen, which still has 2 lone pairs, and 2 more on this side. This still has 2 lone pairs. And that would be our picture of CO2. And again, it is a nice linear molecule because the electrons on the carbon are going to try to get as far away from each other as they can. Now, just the last two. Here's arsenic. Now, arsenic is kind of odd. Arsenic is in family 5. So we go 1, 2, 3, 4, 5. So very much like a nitrogen. Hydrogens we know only have 1. So let's pair up the ones that are half filled. And we'll clean up our molecule, put arsenic in the middle. Hydrogen, hydrogen, and hydrogen. And we still have a lone pair on our arsenic. Okay, here we have iodine. Iodine we know is in family 7, so 1, 2, 3, 4, 5, 6, 7. And here's another iodine. 1, 2, 3, 4, 5, 6, 7. So we can see each of these has 1 electron to share. So we put it together. Iodine, iodine, and each of the iodines has 3 lone pairs. Now I would like to go back just a moment. And we're talking about something called the octet rule. And we can see what happens is this carbon is near 8 electrons. Hydrogen doesn't follow the octet rule. Hydrogen only needs to have 2 to fill its shell. This oxygen here, we can see it's following the octet rule, just as this one is. And this nitrogen has near 8 electrons. So the octet rule is the idea that a lot of times atoms are going to gain or lose or share electrons until they have 8 electrons. Now when we get a double bond, it still has 8 electrons nearby, so this still fulfills the octet rule. And notice that these electrons that are between the atoms get counted for both atoms because the oxygens are near those. Same thing with the nitrogen. Those 6 in the middle get to count for both atoms, so we're still following the octet rule. Over here in fluorines, they're near an octet, and the oxygen's also near an octet. So all of those are following the octet rule. Here we have our carbons, near an octet, and near an octet, and we're not surprised that the hydrogens don't do that. Now even with our 2 sets of double bonds, the oxygen here is near 8, the carbon is near 8, and this oxygen is near 8. Everybody follows the octet rule. Arsenic is near 8, and each of these iodines is near 8. So this has been the how to draw Lewis structures, and this is a character here of Gilbert Lewis, and he was a man who really came up with the whole idea about sharing electrons making a covalent bond. From his work, Langmuir did extra things and then went on to Linus Pauling to get a Nobel Prize on all this information. Lewis taught structures.